Hello, in this video, we are going to cover problem number 4 on the CSM mock final. In this problem, we have some binary tree as an input, and we have to write a function that will check whether the binary tree is mirrored or not. And here we have an example of a mirrored tree. You can see it's basically just a reflection of itself. So if we check these two nodes, the values are the same. And if you check these outer nodes, the values are the same. And same thing if we check these inner nodes. Another example of a mirror tree is here. This is also pretty easy and doable to figure out, I guess, just in that you can kind of tell that this is a base case, since if we draw a line here, then we can see that even though this tree only has a single root and the children are both null values, this is still considered to be a mirrored tree. Some examples of not mirrored tree are here. And in these cases, you can see that one child has a different value from the other child. So in this first one, the left child is null and the right child is 3. In this second one, the left child is 1 and the right child is 2. And what we do is we have to fill in this helper method, which is an overloaded method. It has the same name, is mirror, as the normal method up here that is defined, but it does have different arguments. So we can see that's called with the left and the right children of the root. So based on that, that kind of gives us a clue that we might have to compare the values of the left and the right nodes. And let's first go into the base cases. So looking at the base cases, we have this example here that seems like it might be the perfect base case for when something is mirrored, which is when the left and the right nodes are both null. So we first check if the left value is null. And we also want to make sure that the right value is null. And in the case that both of these values are null, what we can do is we can just return true. So now that we have this base case out of the way, we can tell that there's another base case we have to consider, which is when one of the nodes is null and the other node is not null. And so we have to consider that. And what we can do is we can do this, write this in one single if statement using the fact that the case where both the left and the right nodes are null is already covered by this if statement above. And that also using the fact that we are using an else if, although even if we didn't have an else if, we have a return true, so it wouldn't matter. And the reason why having this case above is important is because what I'm going to write here is left equals null or right equals null. And in this case, we're going to return false. So the reason why this works well, and the reason why it's so important that we have this specific order where we first consider the and statement, and if this is false, then we will consider this or statement, is because this left equals null or right equals null statement is true in these cases. It's true in the case where both children are null, and it's also true in the case where only one of the children are null. And note that when both children are null, we actually want to return true. So what happens is, since we have already had this and case, or this case here where both children are null, covered in this first if statement, we never ever have this if statement be true in this case. It's just simply not possible because this case is always going to be covered by this if statement. Let me change some colors. Okay. And so now we have these two base cases out of the way, and we now have only the cases where neither children are null and they both have some value in them, and the children also might have children of their own. So in this example here, up here, we might have a node here and another node here. But note that for this example, no matter what the values of the children are, so say that the value of the children look like this, no matter what the values of these children are, so basically the children of the children, since the left and the right direct childs, which are of course the ones that are passed in through our argument, because the values of these are different, we have to return false. So that means what we can do is we can check if the values are different. And just to be safe, let's use a dot equals, since we don't know what type the value might be. It looks like it could be an integer, but it could be a string. So we've compared the value of the left node with the value of the right node. And in this case, we're also checking that the values are not equal. So since the values of the left and the right nodes are different, we are going to return false. And now finally, the only case that's left is if the values of the right and the left nodes are the same. So this is the mirrored case. We can kind of imagine that we only are considering these two left and the right nodes, and we're checking if these are the same, and they are the same. So in that case, what we have to do is now we move on to the children of these nodes. And we can see that we have this whole function already written out. So instead of doing an iterative solution, it might be just easier to do a recursive solution where we consider these children and check that these children are the same values. So the innermost children are the same values and the outermost children are the same values. And we can also see that this structure I've talked about, where the innermost children and the outermost children have to the same values, still applies when we have many children. So if I zoom in here and I give all these, like third layer nodes children. So these are the third layer nodes, and we are now creating the fourth layer of nodes here. Let's not give 7 any children, but we're going to give the 3s children. We still have this structure of having the outer nodes be the same and the inner nodes be the same. So we can see that what this means is, in fact, the trees underneath the nodes have to be basically just reversed as well. The trees underneath the nodes are going to be the same values, but mirrored. And so we have this kind of recursive structure where we constantly can just look at these like left and right nodes and check their children. And the children are going to be the same, but mirrored. So that kind of helps inform our final case, which is when the left value is equal to the right value. So the case where it could be mirrored, but we have to check the children. So what we have to do is we have to check the outermost and the innermost children. So maybe what we can do is just check Boolean outermost equals is mirror left dot left. So this is the leftmost child, and we are comparing this with the rightmost child. So right dot right. And then we're also going to find Boolean innermost, which is when we check the innermost child or innermost children with the innermost children. And we want them to be the same or the same value, and for the trees underneath them to be mirrored. So that's our goal. And now we have a choice to make. How do we combine these two innermost and outermost booleans? So what we can see here, let's zoom in again. We have this idea of innermost and outermost. So what we've done is we can basically say we compared this blue section, this tree created by the value 3, with this blue section. And we checked if it was mirrored. And as it turns out, it was. And we also check, let's use the color purple, this purple section with this purple section, and both of them are leaf nodes. Their children are all null. So as it turns out, they're both the blue and the purple sections are mirrored, and so this entire tree can be considered mirrored. However, if instead we have, say, the innermost node here has a child, and this right innermost node does not have a child, this entire tree would no longer be mirrored, which means that both innermost and outermost nodes have to be mirrored. So we can combine these two booleans using an AND logical operator. And that's it. So thank you for watching, and I hope this has been useful.